So, what we have been doing since the beginning is random walks in its various incarnations. So, we started with the discrete random walk, where you could come from either the left or the right with associated probabilities, right? And then we did the continuum limit of that, which was the diffusion equation. Is equal to d del to p del x2. And if there was a bias in the p and the q, then I hope you get this, right, that Vection diffusion equation. And then with the stochastic differential equation form of that, we did the stochastic differential equation form of that, which tells me about the trajectories. So, dx of t was square root 2d dw, the Wiener process, and if I have some deterministic component, then ax dt, where this dw goes as square root of dt. So, in a sense that this is the one stochastic process that we have looked at for so long, half a semester almost, and looked at its various manifestations and applications. What I now want to do is to now take this is a specific stochastic process, this random walk, and generalize this a little, and that is where Markov processes will come in, right. So, this is one example for Markov process, in that when I think about a random walk, every step I take is I choose with these probabilities p and q, irrespective of what has gone on before, right. So, there is no memory to the process. The next step that I take is independent of how I got here. I could have come from there, I could have come from there, but once I am here, I have some probability of taking a step, some delta x in whatever random direction that I choose. Okay, so, this no history dependence, in some sense, no memory or no history. This is a property generally of this class of processes called Markov processes. So, that is what we will try to formulate a little generally, and then look at all the analogues of these diffusion equation and this and so on for a general Markov process. Okay. So, that is the next part of the course, of course. So, it depends only on where you are on that, but it does not depend on how you got here. So, it depends of course on one step memory, essentially just where you were at the previous step, but nothing beyond that. So, single step memory if you want. All right. So, that is the idea. And if you, I have not looked at it yet, but if you have done this assignment problem, how many of you did this memory dependent random walk? Could any of you code? It was, what did you get? Did you get diffusion? If you looked at the x square versus time, but the next part, okay, and hopefully you would have got something which is t to the power of alpha, where alpha is greater than 1. At least I think the values I chose were for super diffusive walks. So, when you incorporate memory, you no longer are guaranteed to get diffusive walks. You can have different sorts of super diffusive or sub diffusive walks. So, but right. So, today I will talk therefore of this general Markov processes where you still do not have memory, just a single step memory. So, here is my basic variable xi of t. Right. So, this is some variable that varies continuously with time. It's a variable varies continuously with time. Okay. And this is some stochastic process. the set of values that this psi itself can take is the set of values that psi can take is my state space, or is called the state space or sample space, and that can be discrete or continuous, state space or sample space, and that can be discrete or continuous. So, for example, when I think of trajectories like diffusive trajectories, particles moving in space, it can access all positions. So, then the psi of t would be the position of a particle undergoing a random walk, and that would be therefore a continuous state space. It could adopt any position. On the other hand, for example, if I am thinking of conformational states of macromolecules, like a protein or something, which can be in some open, let us say an ion channel, which could be in an open state or a closed state. In that case, the conformational, the state space or the sample space could be discrete. So, that depends on what process you are studying. But generally, I call this psi of t as my basic stochastic process. In that your time increments, your time axis is continuous. So, t plus dt, t plus 2 dt and so on. But the state in, so here maybe the state is in if it is an ion channel, it is closed, open, like that. But the time axis itself is a continuous axis of time. So therefore, it can make instantaneous jumps from, let us say, a closed state to an open state. Yes. Or if it's trajectories, it could be continuous. So, depending on whatever is the process. Yes. All right. So, if I want to specify in some sense all the statistical properties. So, if this is some general stochastic process, okay, I have not right now placed any constraint on it. So, if I wanted to specify the general properties of this statistical properties of this stochastic process, I would need to specify probabilities, and in general I would need to specify, let us say, probabilities P1 of it being at some state at some time T1, of it being at some particular state xi 1, then something like xi 2 T2, xi 1 T1, right, that it was at time T1 in state xi 1, but at time T2 it is now in state xi 2, and so on and so forth, all the way up to this nth. So, xi n Tn, xi n minus 1 Tn minus 1, all the way up to xi 1 T1, right. So, this is the n time joint probability distribution, right, that your stochastic process, I sometimes will say particle, but it's in any process, any stochastic process. At time T1 had the value xi 1, at time T2 had the value xi 2, at time Tn minus 1 had the value xi n minus 1, at time Tn had the value xi n. And the way to incorporate that is that if you think about this probability times this z xi 2 d xi n. If it is a continuous process, then the way to think about it is that this is the probability, this was the probability density, and this is the probability for it to have been in the neighborhood of xi 1 at time T1 and so on, in the neighborhood of xi n plus d xi n at time Tn, and so on. Okay. Just in the normal way that we interpret joint probability distributions. So, I would have to know all of these probability densities in order to calculate statistical averages of whatever physical quantity that I want. So, now I have this n time joint probability distribution, right. So, this Pn is a n time joint probability density, and I know that if I have a joint probability density, recall when we were, when I had P of A comma B, a joint probability, I could write it as the product of a conditional probability of A given that I know that B has happened times the probability of B itself, right. So, similarly, this n time joint probability distribution I can decompose into n time conditional, right, times a n minus 1 times joint. So, this Pn of xi n Tn xi n minus 1 Tn minus 1 all the way up to xi 1 T1. So, this is my n time joint probability. I can decompose into one conditional, which is that what is the probability of it being at xi n at time Tn, given that it has followed this particular history, that it was at xi n minus 1 at Tn minus 1, xi n minus 2 at time Tn minus 2, all the way up to xi 1 at T1. So, this is a conditional probability times what is the probability of this history itself, which is n minus 1 time joint probability distribution, right. So, xi n minus 1 Tn minus 1 all the way up to xi 1 T1. Is this fine? So, let me again put a subscript here. This is just a generalization of that statement. Now, in general, of course, for any stochastic process, the probability of it being at xi n at time Tn is a probability of this full history. How did you get to this previous? All of these previous histories in principle can determine the probability of this xi n at time Tn. But now is where we will make the special assumption of this Markov process, where we will say that it does not depend on the full history, but only where you were at the previous instant of time. So, one step memory, right. So, that will simplify my, so my Pn. So, therefore, this Pn of xi n Tn given the full history xi n minus 1 Tn minus 1 all the way up to xi 1 T1, this just becomes a single step memory, that xi n Tn given xi n minus 1 Tn minus 1. That is it. Okay. It does not depend on how you got there, it just depends on where you are now at the previous instant of time. That will determine the probability of where you are. So, this to this. So, this is where this is my Markov property. So, if we have a non-Markovian process like that elephant, that memory wala random walk, then you cannot make this assumption. You will have to work with this full n time conditional and n time joint PDFs. But for a Markov process where you have only a single step memory, this is the correct thing to do. Right? So, this essentially says that the future step is only dependent on the current, dependent on current state and not on the full history, okay, not on full history. All right, is this clear? Once you do this, then you can do this for every one of this. So, now I have broken up this n time into a 2 time conditional. Now, I have this n minus 1 time joint probability. This also I can break into a conditional and a n minus 2 times joint probability, and then the conditional again will only depend on the single time step before it. So, you can do this iteratively to get this n time joint probability distribution xi n Tn all the way up to xi 1 T1 as xi n Tn given xi n minus 1 Tn minus 1 times xi n minus 1 Tn minus 1 given xi n minus 2 Tn minus 2 times all of that, all of these P2s times P2 xi 2 of T2 given xi 1 of T1 times this finally this one time probability p xi 1 of t1, right. So, this I repeatedly apply the Markov property. I can decompose this n time joint probability distribution into a product of these conditionals, 2 time conditionals, and this single time probability of it being at xi 1 at its initial time t1. This is where I get with the Markovian property. Now, I can make some further assumptions. So, now I consider a special Markov process, which is a stationary Markov process. So, now I consider a further simplification, which is a stationary Markov process. Stationary means what? Stationary means that essentially your properties do not depend on time, right, which means that this P1 of xi 1 comma T1 I can write as some P of xi, which is my stationary density, Okay. And further these conditionals, right. So, this P2 of xi comma t, given that you were at xi prime comma t prime, right, this will also only depend. So, you could do a global shift of time, which means that all that will matter if you have a stationary Markov process is that this is going to be a P2 of xi t minus t prime, given that you were at psi prime at time 0. So, all that matters is how much time has elapsed. This specific value of t prime and the specific value of t does not matter. I can translate my time axis. So, all that matters is how much time has evolved from when you were at psi prime and to the target state xi. So, then for this stationary Markov process, then I can write this as this Pn xi n Tn all the way up to xi 1 T1, right, as this product of T psi j plus 1 T j plus 1 minus T j xi j, and a product of these j equal to 1 to n minus 1, right, and then all that is left is just this P of psi 1. So, essentially initially I had, if I did not, for a general stochastic process, I would have to calculate each of these conditional probabilities. Now, if I assume the stationary Markov process, all I am left with is essentially to calculate 2 quantities. One is this P of xi, right, what is the stationary density, and the second thing is this P of xi prime comma t given xi. So, these are the only 2 for a stationary Markov process. These are the only 2 quantities that I need to calculate. Small n, sorry, this n I have to get to xi. Further, sometimes people will make a stronger assumption, which is that you have a lot of mixing, and in that sense this probability. So, this is for a stationary Markov. So, this is for a stationary Markov. Sometimes people will make a stronger approximation of mixing and say that this transition probability P of
xi prime. Let me just reverse the psi prime to xi. P of xi comma t given xi prime will approach P of xi as your time goes to infinity,
which essentially says that if you waited long enough, you lose all memory of where you started out from, and then it just becomes a function of the stationary density P of xi. Right? So, this is like the counterpart of the ergodic hypothesis. If everything is very well mixed, then you just have this P of xi, the stationary density, that will determine all properties of this stationary Markov processes. Okay. All right. So, this is what we will deal with. So, we will talk about not just Markov processes, but stationary Markov processes. Okay. Okay, is this whole formalism clear? So, I want to write down essentially I have this quantity, right. So, I have this xi of t given xi prime, right. This xi of t given xi prime, P of xi comma t given psi prime, given some initial, let me call it xi naught. And I want to know that how do I describe the evolution of this probability? How do I describe the evolution of this probability? So, I was at xi naught, after some time t has elapsed, I am at time xi, and how does this probability change with time? Okay. So, the first step is to write down what is called as the Chapman-Kolmogorov chain equation for Markov processes. So, essentially I can write this as very simply probability of being at psi, right, t minus t prime, given that you were at psi prime at this time t prime, times the probability of that itself. So, psi prime at t prime, given that you had started off at psi naught, and I integrate this over all of these intermediate positions. So, I started off here xi naught. After some time t has elapsed, I reach this desired position psi, and I am looking for this probability P of psi after some time t has elapsed. So, what I do tautologically is to just sort of break this up, say that I have gone to some intermediate position psi prime at some time t prime. Okay. So, that is this xi prime at time t prime starting from this xi naught, and then I have to go from this xi prime to this final desired position xi in whatever is the remaining time t minus t prime, and that will give me the total probability. And then this xi prime, so I can take any path. This is a stochastic process. So, I can go like this, I can go like this, I can go like that, whatever. So, I integrate out over all possible positions of this intermediate position xi prime. So, that is this. Now, this is of course a nonlinear equation, because I had these propagation probabilities of going from xi naught to xi in some time t, and inside also I have these similar quantities xi naught to xi prime in some time t prime. So, these are nonlinear equations, but one can convert it into a linear equation by defining some transition probabilities. So, that is what we will try to. So, this by the way is called is a full name, a full list of people who came up with this formalism: Bachelier, Smoluchowski, Chapman, Kolmogorov equation. Essentially sum over all intermediate, all histories of this stochastic process. So, now what we want to do is that we want to reduce We want to simplify this a bit so that we can actually work with this equation. Please ask if it is not clear, because this formalism of the Chapman-Kolmogorov or the master equation is what we are going to use from now on. Yes. Correct, but essentially this stochastic process is essentially xi of t, right. So, when I say I am integrating out over xi prime, this is xi prime at some instant of time t prime. So, therefore, if you were to reach at this xi prime at some other point of time, then that would be a different stochastic process that you are integrating over. So, yes, you are right, but that is sort of inbuilt into this integration. Okay. So, this is what I am looking at, p of xi prime t prime. All right. So, now let me I want to write down this in a simplified form. Yes. What is independent of the paths? P psi t given psi 0. Yes. No. So, essentially, this probability, that what is the probability that you started out at psi naught and you ended up at psi at some time, is dependent on all the possible paths that you can take to go from psi naught to psi in this time. You could have taken this path, you could have taken this path, you could have taken this path, and so on, right. So, all I am doing is that I am summing over all the possible paths of this process that will take you from this point to this point in this amount of time t. So, if I could just go in two ways, this here one jump like this, another jump like that, this would have some probability p 1, this would have some probability p 2, the total this probability would have been p 1 plus p 2. Similarly, now I have many paths, each of which corresponds to one choice of this psi prime at some particular t prime, psi prime at t prime, and I am summing over all of these possible paths to get what is my final probability. So, now I make this assumption that this t that I have over here, xi of t, right, this t so I have two things, t and t prime, let me very badly call t prime as t and t as t plus delta t. So, I started out, remember, at time 0, I was at xi naught at time 0, at time t equal to 0. Then in some intermediate time t, I have reached xi prime, and then in some final time t plus delta t, I have reached xi. Okay. So, therefore, if I write this is p of xi t plus delta t given xi naught is equal to integral d xi prime p of psi given xi comma delta t, because that is t minus t prime, given xi prime p of xi prime t xi naught. Okay. All right. What do I want to do? I want to write down an evolution equation for these probabilities. How do these probabilities evolve? So, now I have written one part, which is xi of t plus delta t. Next, essentially what I want to write is xi of p of xi comma t. To do that, note one thing, that these probabilities essentially are necessarily normalized. So, these conditionals that I have over here, so p of xi comma delta t given xi prime, right. If I do a d xi of this over all possibilities, this is necessarily equal to 1. So, I was at xi prime, after some time delta t I was at xi, I integrate out over all xi, I must have been somewhere after time delta t, that is guaranteed. So, therefore, this integration must give me a 1, right. This is fine. Okay. So, then once I have this, I can use this to write So, what I want is this thing P of xi comma t given xi naught, right. I have xi of t plus delta t given xi naught. If I write this, I can subtract, divide by delta t, make that a derivative, write down a differential equation for how these probabilities evolve with time. So, this thing is P of the same thing, P of xi comma t given xi naught, right, times, let me use this condition, P d xi prime, P of xi prime, right, comma delta t given xi. This thing is anyway 1. So, all I have done is that I have multiplied this by 1, P of xi, xi prime delta t given xi, integrated out over all xi prime. So, I just multiply that by 1. So, then this has no xi prime, anyway it is a constant, but I will take it inside. So, I have a d xi prime minus infinity to infinity, P of xi comma t given, let me write it the other way around. Let me write that first, P of xi prime delta t given xi, and then P of xi comma t given xi. Okay. So, now what I will do is that I will subtract. So, I have P xi at t plus delta t given xi naught minus P of that thing xi comma t given xi naught, okay, is equal to, both integrals are over d xi prime. So, both integrals are over d xi prime. In one case, I have P of xi delta t given xi prime, P of xi prime given t xi naught minus this P of xi prime delta t given xi, P of xi t given xi naught. I have not done anything, I have just written out the two integral terms. Then I will divide this by delta t in the limit that delta t goes to 0. Therefore, I will divide this by delta t, I will divide this by delta t. What are these? So, these are probabilities that I was at psi prime. After some small amount of time delta t has passed, what is the probability that I am at psi? Now, I am dividing by this by the time delta t time interval. So, these become rates. So, these are now transition rates of going, transition rates per unit time of going from xi prime to xi is this term. So, let me call this, let me write this d xi prime. This is a transition rate of going from xi prime to xi, right, times the probability that you were at xi prime to t xi naught. And this is the reverse transition rate, that what is the transition rate of going from xi to xi prime, right. So, transition rate of going from xi to xi prime times the probability that you were at xi. So, and this left hand side is of course del del t of this P of xi comma t given xi naught. So, I have introduced these transition rates, okay, where this small time delta t by decomposing this hop into a time t and a small time delta t, and this probability dividing by that delta t, taking the limit delta t going to 0. So, I have these rates of going from xi prime to xi and from xi to xi prime, and then I have this equation. This is an equivalent formulation of this, but this has the name, this is called the master equation. This is called the master equation, or more specifically, it is called the forward master equation. If I know these transition rates, then I can in this equation or in so, for example, if I think about if I that's why it's always good to go back to the random walk and think about this. So, I had this, if I was here and I was here at some n at some time t, I could have at time t plus 1, I could have hopped to the right with some probability p and to the left with some probability q in these unit intervals of time, which means that these transition rates in this case for the random walk are p and q, right. So, because these are probabilities per unit time. So, these transition rates are p and q. Once you know these transition rates, you can write down what is the evolution equation for these probabilities and then try to solve the evolution equation for the probabilities. So, what you are saying is that if I know this, I could maybe have written these as well. Yes, it is just that mathematically these are nonlinear equations and therefore getting the solutions of these are more difficult, and that is why I am saying this is an equivalent formulation. There is nothing extra physics wise that has gone in, but these are often the master equation formalism is often the more easier formalism to work with rather than this full Chapman-Kolmogorov formalism. All right. So, if I now stop and think about this equation, what is this equation saying? Okay. It is good to just, because it is a lot of symbols. So, it is just good to think about what this is saying, this forward master equation. Huh? Why do we keep the name? I will, one second, let me just give this and then I will come to that, because it is very important, because I will do the other one as well. All right. So, what I am writing down over here is this rate of change of probability for some state psi, right, given as I naught and so on. And what this is that it's a combination of two things. One is that so you were at some probability of being in some state xi prime, in some other state xi prime, which is this, and then you make a jump from xi prime to xi. So, transition probability from xi prime to xi. So, you were in some different state xi prime, with some probability you make this jump from xi prime to xi, and that adds to your probability of being in this state, right. And you do this and you sum over all possible states you could have been in xi prime. So, these are incoming terms in your probability distribution, right. These are terms that make you gain probability for being in state. Correspondingly, you will have lost terms, which correspond to the fact that in principle you could have been in state probability of being in the state xi already, you were at xi, but then you make a jump out of this state, okay. Transition probability from xi to any other state xi prime. So, you are already in xi, you make a jump to any other possible state xi prime, sum over all of these xi primes, that is your outgoing probability, right. And then your net change of probability is the sum of all your incoming probabilities and your outgoing probabilities, right. So, this first term over here is the gain term. This term over here is your gain term, which is you were at some other state, you make a jump to your desired state, and the second term is your loss term. This term over here is your loss term, that you were in this desired state, but you make a jump to some other state, xi to xi prime. Okay. So, this gain minus loss gives you the net change in the probability of being at that state xi. Okay. This is of course the general formalism. If you in principle, again, so like I said, the xi's could have been discrete variables. So, let me just write it for a discrete variable, that the same thing, but let me just write it anyway. Del p del t of being at state n at some time t, given you had started at some state n naught, is a sum over all gain terms. So, p of n prime comma t given n naught, you were at some other state, you make a transition from that state to n, this transition rate summed over all n primes. This is the gain minus the loss, which is that you were at n, and then from n you make a transition to some other state n prime, and this is summed over all n prime not equal to n. Right. So, in particular, if your stochastic variable is discrete, it can take discrete values rather than a continuous value. This integral just becomes a summation, but everything else remains the same, right. The interpretation of the master equation stays the same. So, these are discrete Markov processes. In principle, you can think of that integral as a continuous Markov process. This is a discrete Markov process. And again, it is good to think of go back and think of the random walk. So, del p n comma t del t for the random walk. So, you could have come, let me take the 1D random walk just for simplicity. You could have come, where could you have come from? You could have come only from the side to the right or the side to the left. Okay. So, if you were the side to the left, n minus 1 comma t, left to right, let me say the hopping probability per unit time is p. So, that would be p plus a q of p n plus 1 comma time. If you were to the right, you hop left with a probability per unit time q. These are your gain terms, minus your loss terms are just p plus q of p of n comma t. You were at n, you could have hopped to the left or to the right. Each of this would be a loss, p plus q. So, this would be your master equation for the one dimensional random walk. Right? What is that? Where is the 1 minus? Here? This fine, right? So, this is essentially what we had written down initially without thinking about master equations and so on, because the random walk process is one of the simplest Markov processes to think about. But in general, this time evolution of the probabilities for these Markov processes is just a gain term and a loss term. And so once you think of that, think of these processes in these terms, that how can I get to this desired state and how can I get out of this desired state? It's very easy to write down these. Master equations and then think about how to solve these master equations. All right. What is the loss term, right? So, here is my random walk. I am thinking about this probability, that the probability that at time t I am at this state n. This is n plus 1, this is n minus 1. So, if you were already here at the previous instant of time, right, you could go out of this by taking a hop to the right or a hop to the left, and this would decrease this probability. The probability of being at n at time t, hops out of this would decrease this probability. Therefore, this is a loss term in this probability evolution equation. So, all terms that take you out of this state, out of the desired state. So, remember I am talking about the time evolution of state xi. So, any hop that takes me out of this state, which are hops like this, hops from xi to any other state xi prime, these are loss terms in that they decrease the probability, and then the summed over all xi prime, this gives me the net loss term. So, this total change in probability comes from this gain minus the loss, and then given a process, you think about what are the possible transitions. For example, for this random walk, there are only two transitions, two hops to the left and right, and you can write down the corresponding master equation. But here this was a discrete time, discrete space walk. So, my time unit incremented by 1, so t plus 1 essentially. So, if I say that these are if I think of the continuous time version of this, the continuous time discrete space version of this, I would say these are probabilities per unit time, and therefore, these would become the rates. Over there, since I said t plus 1, therefore, that probability rate distinction goes away. Yes, yes. These are rates in this formalism. These are transition probabilities per unit time, probability per unit time. But therefore, it is not sum to 1, if that is what you are asking, because these are rates. Here, of course, in the discrete again in the discrete random walk, because my hops were taking place in unit time intervals, the distinction goes away. But in general, these are rates, these are probabilities per unit time. Okay, so therefore, these have so for example, you could say that it is 5 hops per second. So therefore, these have dimensions of inverse time, and these tell you how fast these hopping processes are taking. Okay. Yes. You have to take the limit correctly, of course. So let me just define that, since maybe I have not defined it. So this transition rates xi comma xi prime is the limit delta t goes to 0, probability of xi comma delta t given xi prime divided by delta t. Okay. So the precise definition is this probability per unit time in this limit, in this limiting sense. So in this, so for example, if you are writing sum over all possible xi's, p of xi comma delta t xi prime 1 by delta t, right. This summation is 1. Doesn't matter. In time delta t, I must have gone somewhere. Sorry, I should sum over xi since. So I must have gone somewhere. This is the same as that normalization that I had written down. So this summation is 1 divided by some time scale delta t. So okay, so now what is the confusion? Delta t goes to 0. This is the sum of the rates, yes. But what is the question? Tell me. No, that's okay. It's fine. These rates and probabilities are always confusing sometimes to me as well. But so what is the confusion, if you tell me? 1 by delta t. Okay. Sum of the rates. How is it not 1? No, because See, the way you think about this is that, again, it's a question of how you take the limit. So, you were at some state xi prime, you are going to some state xi within some small window, that is some small probability. Then you divide it by this time delta t, and you take the limit properly such that this is some finite value. What this sum, if you are asking, for example, if I have these omegas and I take this summation of these omegas over all possible states xi, what does this give me? This gives me the inverse of this, these units of inverse time, right, 1 by delta t. So, the inverse of this summation gives me the typical time I stay at that state xi prime. So, I am at this state, I can escape to here, there. What is the typical time I will stay here before I make an escape to any of these other states? So, if that's, so for example, if these rates were 1, 2 and so on, and they added up to 5 per second, all of these rates, that means that I stay at that state for a typical time of 0.2 seconds. That is the typical, the inverse of these rates gives, sum of these rates gives me the typical residence time of staying in that state before I make a escape through a hop to any of these other accessible states. Okay. So, that has some physical unit, because these, the way you take these delta t going to 0, it gives you some finite number, which is some finite rate, but that has a meaning in that the sum over all of these rates gives you the inverse of the residence time of staying in that state. But it's a crucial a to sort of appreciate. If I take the integral over all, sorry, integral over what? All of these states. Why? But these are also small probabilities, right? Well, actually, sorry, thank you. No, because the summation that I take is xi not equal to xi prime. I mean, I'm transitioning from state xi prime to a different state xi, but I could have stayed in that time delta t in wherever I was. So, this is summation over all states not equal to where I was. That need not necessarily be 1. If your delta t is very small, I could just stay, I could have just stayed where I was. Thank you. So, when I said it was 1, it is wrong. It should be actually less than 1. But in some sense that is there, right, because so right now I am talking in terms of rates. Okay, so for the time being, forget this random walk thing. What I have talked about is in terms of rates, and therefore, like Jeremy was asking, if in that time delta t I have summed over all of these probabilities of hopping to everything else, whatever is 1 minus that is the probability of staying there wherever I was. And in fact, that is why the inverse of this gives you the residence time in that state, that how long do I stay there before I make a hop to any of these available states that I have. So, that is implicitly there in these transition rates. Forward, yes, sorry. Why forward? It's forward because you can write a different version of the master equation which is backward. Okay. So, I have this, right. So, essentially what do I have? I have P of xi comma t, given that it was at xi naught at some time t naught. I have suppressed it by saying that time, because there is time translation symmetry, I have called it 0, but whatever I could explicitly call, does not matter whether I write t minus t naught here and 0 there or t naught here. So, I have this thing, right. And now I am asking that how does this evolve in time, right, which is how I have gotten this forward master equation. But I have 2 times here essentially t naught and t. What I have done here is that I have taken a derivative with respect to t, which is the final time. Equivalently, I could take a derivative with respect to t naught, which is the initial time. Okay. So, xi of comma t given xi naught of t naught, same quantity, but I could have taken a derivative with respect to this initial time, and that would have given me some, which is something that we will do actually, that would have given me what is called the backward master equation. So, if you take a derivative with respect to the final time, it gives you the forward master equation. If you take a derivative with respect to the initial time, it gives you what is called the backward master equation. And the backward master equation is very useful to calculate mean times of passage, which is what we will do at some point after the midsem. But yeah, so before the midsem, we will just stick to forward master equation, where you take a derivative with respect to this final time. This forward master equation is what you will most often see in the stochastic process literature. So, if people say without a nomenclature, they will generally mean the forward. It is easy because you have this very nice interpretation of gain terms, which are incoming terms into that state, and loss terms, which are outgoing terms from that state. The backward equation is a little more complicated to sort of interpret in these terms, but it's not anyway. So, we will get to that when we get to that. Okay, but this is the forward master equation for probabilities. One can write down with these equations and then work with these equations to sort of solve whatever stochastic process that you are trying to solve. Okay. So, we have done, let me see, we had, again, if I just go back to the random walk for a bit, P n at time t was P of n minus 1 at time t minus delta t plus Q P n plus 1 at time t plus delta. So, we had this. You can take a derivative with respect, you can take a Taylor series expansion with respect to time and get this, which is your master equation. But here my space is still discrete. So, this is still a discrete Markov process, where I have discrete jumps, I have discrete hops from indices. If I make my Markov process continuous, right, then I should be able to get to. So, I have a del P del T, of course, by taking continuous time and how it evolves in time. If I take a continuous space, for example, for the random walk, I should be able to get to the diffusion equation, right, del 2 P del x 2, which was my continuous space, continuous time limit of the discrete random walk. So, till now the master equation is just discretizing space. It does not depend on whether the state space is continuous or discrete. In particular, if I take that as continuous, I can do something more with this master equation, which is I can derive the general form of the diffusion equation for this Markov processes, which is what I will do next day. It is called the Kramer-Small expansion. So, till now for today, we have just derived a master equation. Next day on Monday, we will do the Kramer-Small and therefore derive the analog of the diffusion equation for this for a general Markov process, which is called as the Fokker-Planck equation. Again, you may have heard of it, which is the Fokker-Planck equation. The diffusion equation is just a particular example of Fokker-Planck equation for the random walk. So, we will derive the Fokker-Planck equation on Monday, then we will stop, and on Thursday we will work out some examples of this again this master equation, the Fokker-Planck equation in the context of biological systems, so that you have some practice before the midsem. Okay. Maybe what I will do is that I will upload an assignment on Monday, and you can try, and anyway we can discuss those assignment problems only we can discuss on Thursday, so that because you won't have time to do and submit before your midsem. But so midsem will be this up till this Fokker-Planck equations, and we'll see. We'll continue after midsems.